gonna mute all of you, and the session chair and the presenters can unmute themselves.
Okay, sounds good. So welcome to the session on mobile apps. And in this session, we're going to have 3 presentations. And each presentation going to about 70 minutes presentation, and about 3 minutes we're going to have for question and answers. So make sure to utilize our Slack channel to post your questions here, which I will read to the presenter at the end of the talk. So, the first paper is detecting and diagnosing energy issues for mobile applications, and Julien Lee is going to present his talk now. So you can start sharing your screen.
Okay, great. Thank you. Okay. Thank you very much. So yeah, I'm Xueliang Li, the co-author of this paper. And now I will introduce our work on detecting and diagnosing energy issues for mobile applications. I think most of us have the low battery anxiety. One report shows that 32% users will drop everything to head home and charge phones, and 17% of males mismatch on dating application because phone died, and 6% have blamed the dead phone for not speaking to a loved one. The situation is very serious. We have to take action. But before taking action, we should think about exactly who causes energy waste. It is software or hardware. And the literature has shown that most energy issues are caused by applications rather than hardware and systems. So based on this observation, we will first conduct an empirical study to learn the characteristics of energy issues. And then we will propose a testing framework for detecting energy issues. And at last, we will evaluate our framework. So the data source of our input studies from 3 open source software hosting platforms, namely they are GitHub, Firefox, and Chrome. And totally we have 27 applications. And in these 27 applications, we found 171 energy issues out of more than 100,000 issue reports. Here shows an example of the issue reports. In the body part, it shows the steps to reproduce the issue and the symptoms of the issues. And the developers can also make comments on the report and propose patches to fix the issues. So by reading those 171 energy issue reports, we are trying to answer 2 research questions. The first one is, what are the common root causes of energy issues? And the second question is, how do energy issues manifest themselves in practice? That means, how are the energy issues being triggered in practice? For the first question, what are the common root causes of energy issues? We found the major root cause is the unnecessary workload. We also have excessively frequent operations and wasted background processing and no sleep. And for the second question, how do energy issues manifest themselves in practice? We have simple inputs and special inputs. The simple inputs means that whenever the user simply open or close the application, and the energy issue will be triggered. The special inputs means that only a long sequence of taps or swipes can incur that issue. We also have special context. They are external factors rather than user inputs. For example, the location of the device or the network signal of the device. So based on our empirical study, we have 2 key findings that will inspire the design of our testing framework for detecting energy issues. The first finding is about the root cause. We found that
Elena, can you hear?
So shall we then start live the recording?
Yeah, we will do that.
Okay, let's start recording from slide 10 if it's possible.
Okay, I'm going to do that.
Okay. So our speaker has some technical issues, and we're just going to start replaying from the place where the speaker ended. So it's about slide 10. So it may be like 4 minutes in the presentation, I think.
Sorry, I'm back. Hello.
Oh,
Okay.
Oh, I'm very sorry. So the signal of network is really very important.
do you want instead just play your presentation and after that going to answer questions? What would you prefer?
Okay, I think I can finish it, I think, yeah.
Okay, let's try it.
I'm very sorry for that, and I will go back. So
Okay.
can you see the screen? Okay. So yeah, the previous technology cannot deal with the unnecessary workload and unnecessary frequent operations because the unnecessary workload and excessively frequent operations will increase the energy consumption and the hardware utilization at the same time. So they did not change the U ratio. So the previous technology cannot deal with these two root causes. And also the previous technology cannot deal with the spatial context because they didn't know that the spatial context accounts for such a large part of energy issues. So to deal with these two problems, we have two solutions. The first one is we will use machine learning algorithm to classify our workloads and further assess their necessity. And for the second problem, we will devise two types of most common spatial contexts for effectively revealing them. So we will integrate that two solutions into the whole picture of our testing framework. The overview of our testing framework is showing in this flowchart. The basic idea of our testing is that we test the application with a large variety of input sequences and runtime contexts. So we have 5 steps in our testing. First, we prepare the input sequences and runtime contexts, and then we select a pair of them and run the application with them. Meanwhile, the device is measured by the power meter. At last, we will identify the energy issues from power traces. The first 2 steps, the preparation and selection of input sequence and runtime context is very important because they determine the efficiency of our framework. The last step, identification of power energy issues, is also very important because even though we have triggered the energy issue by using our selected input sequence and runtime context, but it's still a challenge to identify whether they really occurred. So the identification of them deals with this problem. So we first talk about the preparation of input sequences and runtime contexts. The problem of preparation of input sequences is that the amount of input sequences is very huge. So how to effectively explore them? Our idea is to find the most likely energy consuming input sequences and test them first. So we use the event flow graph to help us achieve this purpose. So in an event flow graph, one node is an UI component, for example, a button or a list item. So if the user taps on an UI component and another UI component will be triggered, then there should be an edge from the former UI component to the latter UI component. So in this example graph, we can see 4 input sequences. So if we look into the input sequence, the execution of the input sequence is actually the execution of a path of source code. And the source code is made of basic operations and system APIs. So, and the literature has shown that the major energy consumer in the application source code are of these 2 parts. The first one is control flow operations, and the second one is system APIs that are dealing with the key hardware controls. So based on this analysis, we will use weight to indicate the potential of an input sequence to cause energy waste. And we use this equation to calculate the weight. S is the number of a certain set of system APIs, and C is the number of function invocations. And alpha beta are used for adjusting the influences of them. So in our test, one input sequence with a larger weight has a higher priority to be tested. And a part of weighted input sequence that we just introduced, we also designed random input sequence to cover some exceptional cases we might not envisage. We also prepared our runtime contexts, include normal runtime context and network fail context and flight mode and non-background. So we have prepared our input sequences and runtime contexts. Now we select a pair of them. The objective of our algorithm is to increase the possibility of triggering energy issues. And here's the flowchart of our algorithm. We have 2 types of input sequence and 4 types of runtime contexts. Now we select a pair of them and run our application with the selected input sequence and runtime context. And if there does not have an energy issue, then we simply start a new test case without giving feedback. And if there does exist energy issue, then we increase the possibility to select, for example, that type of input sequence that just triggered this issue. And we did the same to the runtime context. So our evaluation shows that this feedback mechanism can effectively help our testing lead our testing to a very high possibility to trigger energy issues. So now we talk about the identification of energy issues. We first divide our test cases into 5 stages to help us identify energy issues. Namely, they are pre-off, idle, and execution, background, and screen off stages. In the pre-off stage, the screen is off and only the operating system and several built-in applications are running at the background. And to enter the idle stage, we turn on the screen. And to enter the execution stage, we open the application and run the application with the selected input sequences and runtime context. And then we press home button to put our application into background. And now we are at background stage. And later the screen will be automatically turned off. So we enter the screen off stage. So this stage division can help us identify 3 types of energy issues. The first one is execution issue. They are caused by unnecessary workload and excessive frequent operations. And we also can identify background issues caused by wasted background processing. We also can identify no sleep issue caused by no sleep. So the key point to identify execution issues is to assess the necessity of workload. And our approach, our solution is to compare the energy use of all test cases in the same APP category and judge the outlier level energy use as the unnecessary workload. Our motivation is that usually the normal use of energy can satisfy users. If the energy use is at outlier level, at a exceptionally high level, then it's suspected of suffering of energy issues. So the next question is how to identify outlier level test cases. We use the dbScan clustering algorithm to help us identify them. We have 4 criteria, 4 dimensions for the clustering. The criteria are LCHPP, NCHPP, MuSHPP. So based on these 4 criteria, we can identify the outliers. And this left side diagram shows an example. It's in 2-dimensional space. In practice, we have 4 dimensions, but here's an example to show how to identify outliers. We can see that the outlier test case has a very high NCHPP and LCHPP compared with the normal test cases. So how to identify background issues? Our idea is to compute the dissimilarity value of the idle and background traces, because if the power trace is without energy issue, then the power trace at idle and background state should be very similar. If they are dissimilar, then they probably have energy issues. And we did the same to the no sleep issue. And we also conduct an experimental evaluation on 89 applications. And in these 89 applications, we detected 83 energy issues. On average, their energy waste is around 100%. We also compare our testing framework with the previous technology. We use the U ratio to compare them. You can see that our testing does much better than the previous technology in all kinds of energy issues. We also analyze the issue cause and the manifestation in our experiment, and our experimental results justifies our empirical findings. So thank you very much. I think the time is.
Thank you. Yeah, thank you for still being on time. And so please ask questions on the Slack channel if you would like to Julian to answer you. So so while people type in question, maybe I can ask you a couple questions. So my question is how effective your technique is identifying those problematic issues. So how fast you can discover that there is an issue with application. So how many of those test cases do you need to generate?
How many? Actually, we have more than 80,000 test cases.
But but how many do you need to generate before you see there is a problem with application?
Sorry.
So how many? Because your framework is an iterative framework, right? You generate your test case, you look whether there is issue with application, right? And if there is no issue, you'll generate a new test case.
Yeah.
Yeah. So how many of those iterations do you need to do before you actually see something wrong with application?
How many scenarios I have to?
How many times do you need to iterate through this framework loop before you can see something wrong with this application?
Because we test our application with a variety of input sequences and runtime context. So at any time, the energy issue could be incurred, could be triggered.
Do you need to try a lot sequences before you find issue or not?
Maybe the first test case can trigger energy issues, and that type of even though in this situation we will analyze the category, the type of the test case, the first test case, and in the rest of the testing we will use more likely that the type of the first test case we use that type a lot. With a larger possibility, to test our application in the following procedure, testing procedure.
Okay. So we have a question from Said. He says, thank you for nice presentation. So the question is, where is there issues you detected but could not find out the root cause of the source in the source code? So you saw something wrong, but can you actually identify in the source code what's wrong with that? Yeah,
actually, the main concern of our work is about detection of the energy issues. So for fixing the energy issues, it's still a challenge. But in the practice of the developers, they can use for example, there's a tool called CPU Profiler. It can analyze the time usage of the methods in the source code, and this level of information, the method level information of the execution of the source code, is very helpful for developers to localize the energy issue and fix the energy issue.
But they can use your test input, right, to user profiling.
Actually, our work is not about profiling the.
Oh, but they can use your test case that you generated, right?
Oh yeah.
Yeah, to actually see that test case going to trigger code issues in the code after that user profiler.
Yeah. So our work is first to detect the energy issue, and then the developers can look into the test case and profile the execution of the source code and try to fix the issue. Yeah.
So any other questions? Okay, I think we don't have any questions. So we can move to our next presentation then. So the second presentation, it's automated classification of actions in bug reports for mobile apps. And Minju Shen is going to present her, but actually we're going to play a video of this presentation, but the speaker will be available to answer question after the presentation. So we can start playing that. Okay, thank you.
Good afternoon, everyone. I'm Mingzhu Shen from Beijing Institute of Technology, China. I'll introduce our paper, Automated Classification of Actions in Bug Reports of Mobile Apps. This is the outline of my talk. First part, the problem. Mobile apps are the key of mobile device, like mobile phones, and they are playing a key role in our daily life. To this end, developers have designed and implemented a larger number of mobile apps. For example, there are millions of apps on Google Play. Although mobile apps are popular and well acknowledged, mobile apps often contain defects, and such defects could frustrate users, sometimes making them crazy. Once a defect is encountered, users may commit bug report problems to developers. This is an example of bug report. A bug report includes software's expected behavior, actual behavior, and step to reproduce. Step to reproduce describes the operation steps for users to reproduce the reported problem. Step to reproduce is often called S2R for short. Given a bug report, the developers should validate the reported bugs according to S2R. Once the validation succeeds, the developers should fix the bug. Notably, manual validation of the reported bugs is often time-consuming, so automated validation of the reported issues is highly desirable. To this end, a few tools, like Yakusu and Residual, have been proposed recently to validate reported defects automatically. To validate the defects according to S2R, they identify actions in bug reports. They usually leverage a static vocabulary that contains a list of potential action words, like click, tap, press, and select. This vocabulary is built manually. Based on the identified action words, they search UI elements that are associated with the action word. Finally, they generate test cases based on a sequence of action words and their associated UI elements. Evaluation results suggest that such approaches are often accurate, and they can automatically validate around 60% of the defects. We analyze the reasons why they fail on the other, around 40% of bug reports. The first reason is that the static vocabulary they employ may not cover all potential action words. This is a real bug report we extract from GitHub. In this example, we notice that the report leverages 3 different words, select, click, and press, to describe the same action, click. Because people may use different words to describe the same action, it's challenging to collect and classify all potential action words manually. The second reason is that the same word may have different meaning in different bug reports, and thus belongs to different categories. Here is an example. By saying change device language, the developers may describe or click on the language list. Change app name in settings means the user should type in a new name for app. Change orientation is to rotate the device. Such polysemics make it difficult to classify action words solely based on the words themselves. Their context should be considered as well, but static vocabularies do not take such context into consideration at all. Because of the reasons we discussed so far, existing tools often miss action words or misclassify action words, which in turn results in failure of the automated validation of bug reports. To this end, in this paper, we propose an automated approach to identify and classify action words in bug reports without manually created static vocabulary. The second part, solution. Recently, natural language processing has achieved significant advances. We also noticed that bug reports are specified in natural language. Consequently, we may leverage the most advanced NLP techniques to identify and classify action words in bug report automatically. As illustrated in our previous example, we noticed that action word itself is often insufficient to determine the action type. Consequently, we should leverage their context as additional features. Because different UI elements may support different categories of actions, and thus the UI elements associated with the action word could be beneficial for the classification of action words. As a result, our approach leverages the action word, its including segment, name of its target element, and the type of the element. This is an overview of our approach. It takes bug reports as input. Three main steps of the approach are bug analysis, retrieving types of target elements, and machine learning-based classification. Finally, it results in a trained classifier to identify and classify action words. We'll introduce each part in detail in the following slides. Bug analysis is to decompose ISSTA into segments. For example, in this sentence, price a customer server and input an invalid server address should be decomposed into two segments. Price a customer server, input an invalid server address. Segment represents individual actions in production or report. For each of the resulting segments, we leverage NLP techniques to identify action word and potential UI elements. For example, from the segment price a customer server, we should identify action word price and its potential UI element, a customer server. We leverage post-tagging and dependency analysis to parse segment. Post-tagging is a process of marking up the words in a text or corpus as corresponding to a particular part of speech, based on both its definition as well as its context. That is the relationship with exchange and related words in a sentence. This is an example of dependency tree. From the tree, we locate the verb, the root of the tree, as action words. We select the known phrases associated with the verb as target UI elements. Retrieving types of target UI elements is to take input of segment, its action word, potential UI elements, and app. This step is used to find the type of potential UI element according to APK. We encode the information in the bug report into a vector. We also leverage static analysis and collect all UI elements in the app and encode such UI elements into vectors. Based on the vectors, we map your element descriptions in bug report to element in apps, and finally, retrieve the element types. The last phase leverages machine learning-based classification techniques to predict the type of action. It takes input of an action word, its URL elements, the type of its target elements, and its enclosing segment. Output the classifier is the type of action word, and the classifier is logistic regression. The training data are often significantly imbalanced. As a result, the resulting classifier could be biased against minor categories and becomes inaccurate in classifying such minor categories. Considering the imbalance of data, we compute weights for each labels and optimize the training process with weights, where WTI is the weight for category CI, and item number is the number of times belongs to CI. According to the definition of the weights, the smaller a category is, the larger its weight would be. The third part is the result of our evaluation. We introduce our dataset first. The dataset is composed of 3 parts. The first part of the dataset is 39 bug reports collected by Fizini, noted as ISSTA data. The second part of the dataset is 15 bug reports created by Yu Zhao for the evaluation of residual, noted as EC data. The third part, noted as new data, we collect such bug reports from GitHub that contain Android and reproduce. To train the classifier, we manually labeled 1,202 action words from 525 bug reports that are associated with 207 apps. We have a total of 6 research questions. The first research question: is the proposed approach accurate in classifying actions in mobile apps bug reports? We conducted 10-fold cross-validation on that we created manually. From this chart, we observed that Maca was highly accurate and stable, with an average that up to 96.6%. The results of the cross-dataset evaluation also suggest that Maca was accurate. We observed that training Maca with new data and testing on ISSTA data or EC data resulted in high accuracy. We also analyzed the performance on different categories. We observed that Maca was accurate for all the categories. Chart on right is removed the weights. We could find that displacing the weight resulted in significant reduction in accuracy on small number category, such as rotate. The second research question: is Maca accurate in identifying and classifying action words that are unseen in training data? Unseen token means that action words never appear in training data. From new data, we identified 20 rarest action words. 18 of them appeared once, whereas the other 2 appeared twice in new data. Removed them from train set. Thus they were unseen words for Maca trained, then predict it as test data. Evaluation results suggest that Maca has the potential to identify and classify unseen action words, which is a significant advantage over predefined static vocabulary. The third research question: what extent do different classification techniques affect the performance of Maca? We replaced the logistic regression-based classifier with other common classification methods and repeat the evaluation. We conclude that the Maca outperformed alternative classification methods for our task. Also, deep learning resulted in lower performance compared to logistic regression. We think the reason is that deep learning often requires a larger number of training data that were not available for our task. If we can expand the training dataset, it has the potential to outperform logistic regression. To validate the potential of deep learning, we depict the quantitative relation between size of labeled data and the performance of deep learning. From this chart, we observe that the performance increases stably with increased dataset. The first research question: what extent do the context of action words affect the performance of Maca? From this table, we observe that disabling any of the context resulted in significant reduction. If you delete multiple features, the effect will be reduced even more. In addition, type of target element was critical for the performance. The fifth research question: what extent can Maca improve the performance of automated bug report validation by integrating it into existing approaches, such as residual and Yakusu? Maca significantly improved the performance of both tools. It has a relative increase of 22.9% on Yakusu. The same was true for residual for 22.7%. The sixth research question: does Maca outperform keyword match method based on predefined vocabulary? We conducted tenfold cross-validation and built a static vocabulary of action words according to training data. If a word belongs to different categories, we classified it into category it most frequently belonged to, then classifying test data with resulting vocabulary. From this chart, we observe that concerning accuracy and micro-FE, our approach outperforms existing approaches. Now, we have some conclusions. Predefined vocabulary is limited if the word is new or pleases me. Context of action words are critical for the classification of action words. The proposed approach significantly improves the state of the art. In the future, we plan to expand the manually labeled training data and extend the proposed approach to handle bug reports of traditional GUI applications, such as Windows applications. That's all. Thanks for listening. Does everyone have a question?
Well, thank you for the presentation. So, Minju, you unmuted yourself, right?
Yeah, I can hear.
Okay, so if you have questions for this presentation, please type it in Slack channel. So, so the question is,
I'm sorry, I can't hear. Oh yeah.
Can you hear me now?
No. Okay.
Can you hear me now?
Yeah.
Okay, so so while people try typing questions in the Slack channel, I'll maybe ask you maybe a couple questions. So.
I'm sorry. My network is very poor, so if possible, could you?
Do you want me to type the questions on the Slack channel?
Yeah. Okay. I can see the channel.
Okay. So I'm going to type the question. I'm going to just repeat the question. So would it work for regular applications? Can you see my question?
Yes, our approach is also work on general software, but our bug report is only based on mobile apps. So in the future, we may expand our approach on general software because so many softwares has different action. So the bug report is bug report is work on mobile apps now.
Okay, so I think, so here's another question from Matia. So I'm going to did you check the improvements statically based on the bug reports? Did you? Can you answer this question, Minju?
We run the we run the tools the Yakusu and residual but we run the both of the tools on our computer and run sometimes because each app need different app name and have some different, so we must run one by one.
Okay, so I think we ran out of time for this application, so you can definitely answer questions of Matia on the Slack channel if you want to continue that conversation. So we'll move to our last presentation in the session. So the presenter is Oliviero, and the presentation is data loss detection, automatically revealing data loss bugs in Android apps. So this paper won Distinguished Artifact Award, and it's, of course, it was the artifact was evaluated for functional and reusable. So definitely you can run it, and seems like it's quite easy to do so. So Olivier, you can start presenting.
Yeah, thank you. Thank you to introduce me. Can you hear me? Yeah.
Yes, you.
Okay. Okay, today I'm going to talk about DLD, that is a new technique that can reveal data loss bugs in Android application. This is a joint work with Simone Paolo Mottadelli, Claudio Rota, Daniela Micucci, and Leonardo Mariani. Android apps are composed of several components called activities. An activity implements a screen in an app and is responsible for managing the interaction with the final end user. Usually when we use an Android app, we switch from one activity to another in order to use the app functionalities. Sometimes activities are destroyed and recreated. For example, when they are not used in order to release system resources, or when device configurations change at runtime. In this case, activities are recreated to adapt the app to the changed configuration. For example, if you rotate the device screen, the activity is recreated to load the best layout for the current screen orientation. To properly manage the recreation of an activity, the app must first save the state of the activity before its destruction. Once the activity is recreated, the app must restore the saved state. Now let's see an example. We are interacting with an activity that contains free text field, and we have written text in all the text fields. Now we decide to rotate the screen, and so before the system destroys the activity, and the app saves the text field values. Then the activity is recreated in order to load the landscape mode, and the saved values are restored in the corresponding text fields. If the app doesn't handle these activity recreation events correctly, we say that the app is affected by a data loss problem. For example, if the state of the activity is partially saved, obviously when the activity is recreated, the app cannot restore all text field values. And this requires the user to type the text again, which could be frustrating for the user. In fact, as shown in this slide, data loss issues can have an impact on the user experience. Here you can read the 3 real-world reviews of 3 different apps. In the best cases, the user has to enter the loss values again. But in the worst case, the data loss problem evolves into an app crash, as reported by one user. In fact, they say that every time I rotate the screen, the app exits saying file could not be loaded. In our previous study, we found that data loss problems are very common in Android apps. We analyzed bug reports of open source apps available on a well-known app market called Android, and we found that 20% of these apps have at least one bug on data loss. A similar study confirmed our finding on the pervasiveness of these problems. Amalfitano et al. Have manually tested the apps available on Android, and they found that almost 90% of these apps suffer from data loss. This means that current testing practices are not enough to detect this kind of problem. To the best of our knowledge, there are some techniques for data loss detection, but they suffer from limitation in terms of automation, ability to inject events that cause the data loss, and the ability to detect data loss. To overcome this limitation, we have developed a nomadic technique, the DLD, that can effectively reveal data loss problems. DLD interacts with the application under test by performing events on the GUI, for example, touching a button or typing text in a text field. DLD, while interacting with the app under test, builds a model of the GUI that is used to guide the test process. This is a graphical representation of the model. A state in the model is defined by the elements called views that make up the GUI and by the sets of action that are enabled in the current GUI. The idea is to distinguish states not according to the content of the screen, but according to the set of actions that are allowed. And so two different texts in a text field produce two different states only if one of the two values enable new or different actions. This level of abstraction allows not to waste too much time in testing an activity. An event in the model is defined by the type of action that can trigger the transition from one state to another, such as touch, the view on which the event is performed, and the ADB command used to execute the event on the device. The three main features used by DLD to effectively detect data loss are a bias model-based exploration, two data loss revealing actions, and two specific oracles to detect data loss. The bias model-based exploration of the GUI aims to increase the probability of exploring states that may expose data loss. The basic idea of such exploration is to perform new action that can lead to new states potentially affected by data loss. In particular, every time an action to be performed must be chosen, DLD chooses with epsilon probability a random event, and with probability 1 minus epsilon an action that has never been performed before in the current state. For example, assume that epsilon is equal to 0.1, DLD will choose an action not yet executed with probability 0.9, and any action enabled in the current state with probability 0.1. Suppose DLD is in a new state where it can perform 3 possible actions. Since this is the first time DLD is in this state, each event will have the same probability of being chosen. Suppose DLD chooses the action that touches the OK button. Now, the next time DLD visits the state, the action that touches the OK button will have less chance of being chosen. Now, suppose that DLD clicks on the menu soft key. Now, the next time DLD will visit this state, the action that will be chosen most likely is the only one that has not been performed, that is the touch on the no thanks button. In this way, DLD is leading the exploration towards the discovery of new states that may be affected by data loss. In order to produce a data loss, DLD can perform 2 data loss revealing actions. One is performed systematically every time a new state is visited, while the other one is performed randomly in each state. DLD performs the systematic action in new states. The action is composed of a sequence of steps. First of all, DLD interacts with all input views of the activity. In this example, DLD types the text in all 3 text fields. Then DLD performs a double rotation of the screen. The screen rotation is an event that requires recreating the activity. And so if you run it twice, the state before and after the double rotation should be the same. If this is not true, then DLD has detected a data loss. Systematic action can detect a good number of data loss, but there are some corner cases that it cannot detect because they require a particular sequence of action to be detected. For example, in the taskbar app, recreating an activity produces a memory leak. And only after rotating the screen several times in the same activity, DLD can detect an app crash. And so, to handle these corner cases, DLD adds a double rotation to the set of action that can be randomly performed in each state. To detect a data loss, DLD uses 2 types of oracles each time a double rotation is performed. The snapshot-based oracle that takes a screenshot of the app before and after a double rotation and compares the images to detect a data loss. If the images are different, then there has been a data loss. The property-based oracle collects all the properties of the view that make up the GUI and check if they have changed after the double rotation. If only one property has changed, then there has been a data loss. DLD uses both oracles because in some cases, like the data loss shown in this slide, the snapshots are different, but the properties are not. And vice versa, as in this data loss, the snapshots are the same while a property is changed. In this case, the property that is changed is the content description. In the evaluation, we addressed 5 research questions. In RQ0, we analyzed the impact of epsilon in the bias model-based exploration. In RQ1, we studied the effectiveness of DLD in detecting data loss. In RQ2, we compared the DLD with the state-of-the-art techniques. In RQ3, we analyzed the compromise between snapshot and property-based oracles. In the last research question, RQ4, we study how developers react to data loss problems in the labs. For the evaluation, we used a benchmark containing 54 app releases that are affected by 110 real data loss. And we ran DLD on each release 3 times for 3 hours. I will now show the results of research questions in green. For the other research question, you can check the paper if you want. For the research question 1, we'll answer DLD on the benchmark apps to see if it can detect the 110 real data loss. And DLD was able to detect 83 out of the 110 data loss, and DLD was able to find 267 new data loss. And 90% of these data loss has been confirmed by developers to be a bug. In RQ2, we compared DLD with Alaric, which is a mostly random test case generation technique that, like DLD, uses double screen rotations to detect data loss bugs. And DLD was better both in terms of data loss found and also in terms of spurious violations. In the paper, you can also find a comparison between DLD and Quantum, which is a partially automated test technique that can reveal data loss. In the comparison between the 2 oracles, we can see that a large part of the data loss was detected by both oracles, 73%, but there are 27% of data loss that require a specific type of oracle to be detected. 9% require a snapshot-based oracle, and 18% require a property-based oracle. In terms of spurious violations, the property-based oracles are more effective than the snapshot-based oracles. In fact, only 0.1 of these spurious violations are produced uniquely by the property-based oracle. In conclusion, we have developed the DLD. It is a new technique that is able to detect data loss in Android apps. In order to effectively detect data loss, DLD exploits a bias model-based exploration strategy to discover new states potentially affected by data loss issues, 2 data loss revealing actions, and 2 app-agnostic oracles. The experimental results have shown that DLD is effective in detecting these problems, and DLD outperforms competing approaches in doing this. If you are interested, you can download the DLD at the link that is shown in this slide. Thank you for your attention. Hi.
Thank you, Olivier. It was a very nice presentation. So I encourage our viewers to type in questions so we can start a discussion. So the question, I can start with a question. So what I have is maybe we need to have a better Android API to let developers know that some parts of the state hasn't been saved, especially when you do the rotation. Do you have any insights on that?
Yes, Android provides some API that you have to override to save and restore the states. But most, sorry, maybe I didn't understand.
But can you make Android API better to enforce maybe stricter rules on saving and restoring state?
No, because most of the time depend of the application. And so most of the work is in charge of the developers of the app. And it's difficult to specify an API that can be avoided or can limitate these problems in the Android systems. But also in the iOS system, it's the same.
Thank you. So we have a question from Mattia. So he thank you for the talk. And can you tell a bit more about the nature behind the false positives? Maybe screen similarity comparison. What about intentional data loss? So and maybe the GUI in landscape mode is very different than there is an intentional data loss. So
yes,
see this question Slack too. So
yes. Okay, obviously we don't compare the portrait mode with the landscape mode. We just make a double rotation. We rotate the screen and then we rotate the screen again. And so we compare a portrait mode with a portrait mode. And so what we expected is that the state should be the same. Obviously, there is some problems related to some apps that we tested. For example, there is some apps that has a timer, and so it's difficult. Every time we rotate the screen, there is a data loss because the time change. Obviously, we have to improve the technique in order to detect these cases where the screen are different because the app requires two different screens. Yes, and so we think to work on this direction also to avoid the situation in which we have ads. And so if you have ads, the ads can change this rotation. So we can also to avoid this situation in the detection of this data loss.
Well, thank you so much, and maybe you can take it to this material live, and I can continue if he has more questions. Continue that. So I think we concluded with our mobile app session. So thank you so much for everyone who joined us and posted the questions. So and I think the next section is going to be like in 5 or 6 minutes.
Okay.
So we can go into break, right?